Here we go. Now, ladies and gentlemen, raise your hand if you think, after discussing it with your groups, you think that independent events are always disjoint. How many of you picked always? All right, so we've got, okay. Raise your hand if you think it's always. It doesn't matter what other people, whether they raise their hands or not. So we got 5, 6, 1, 2, 3, 4, 5, 6 people said always. Okay, raise your hand if you think it's sometimes. 1, 2, 3, 4, 5, 6. How many of you think it's never? Does anyone want to go in the never category? Okay, the answer is never.
Oh, yes.
Such a bad.
Okay, nobody got it correct. You know what? The reason this is our first example is because the number one most confusing thing in Unit 6 is that students come into it thinking that independent events are synonymous with disjoint events. And six of you said, yeah, they're always the same thing. You thought they were synonymous. Some of you thought there was an overlap, but in reality, if two events are disjoint, there's one thing you know for sure: they are not independent.
Wait, why?
So today, we need to separate out in our minds the concepts of disjoint and independent. That's the focus of today's lesson. We're starting with the hardest part. And then once we get that straight, then everything else will flow in this unit. Okay, so let's start with number 1. And we're going to get off of the Titanic for a second, and let's get into a new context. Let's go into the context of playing cards. So, I know not everyone is equally familiar with American culture. Nick, come on in. Welcome. Yeah, got it. Hey, we got 2 handouts for you. Come and get them. And Nick, and you can just sit next to Andrew. We'll make that group today. It's kind of like the special last day before Thanksgiving groups that we don't have on any of the other days.
What? Except maybe the day before Kennedy.
Except maybe one other day. All right. So, Nick, what we're going to do is find out whether or not disjoint events are the same as independent events. A lot of people thought they were the same thing. Most people get them mixed up in their mind. So here we go. Here's a real world situation. So, ladies and gentlemen, let's regroup. We've had a lot of experience with independent events in this course. We've talked about we've imagined how on a shipwreck you would want there to be a situation in which survival is independent of class. You would want the event alive to be 32%, or the probability of alive to be 32%, whether you're in first class or second class or crew. So, by the way, just the quick argument. Suppose probability of alive is 32% on the Titanic. What if the probability of alive given first class is 32%? Probability of alive given third class is 32%. How are you feeling about this?
Good.
That's a good thing. Now, are alive and first class disjoint? Suppose alive and class are independent. Are alive and first class disjoint? No, they're not disjoint. So there's an example just right up front, based on something with which you're already familiar. That's possible for two things to be independent, but not disjoint. Disjoint means no overlap whatsoever. There's nobody who's alive who's also in first class. No. No, we have overlap between alive and first class. So right up front, that should indicate to you that if you were thinking that disjoint means independent, no, those are actually different concepts. Now let's find out why it is that if you have independence events, or if you have disjoint events, then that never means independent. So, yep. On your example, I just would like you to write down the truth, and then I'll try to explain why this is true. By the way, you do need a picture of disjoint, but I want to make sure that you have a picture of not disjoint in your mind. If two events are not disjoint, then I can tell you for sure what's going on. There's an overlap between them. There's a football that is formed. That's what we informally refer to as the name of the shape when A and B have overlap. We're going to call that the football in there. For those of you who have never seen an American football game before, they play with a ball that's shaped kind of like, this would be the top view of the ball, shaped kind of like that. It's a football shape.
You watch the game last night, Mr. Williams?
This would be more like a European football shape. Okay, so it's American football, European football. I'm sorry, someone asked me a question.
Did you watch the game last night?
I heard it was 105 points total, and I did not watch it. I was doing other stuff last night. But did you watch the game?
Oh, yeah.
Must have been pretty exciting, huh?
It was.
A lot of scoring,
Okay.
even some missed extra points. At least one missed extra point. All right, so here we go. Here's the truth: independent events are never disjoint. Independent events are never disjoint. Provided that the probabilities of A and B are both non-zero. And the other thing that's always true is that disjoint events are never independent. Disjoint events are never independent. Okay, so now we're going to look at some numeric examples in a different context, because the Titanic is not the only context for studying probability and independent events. So here we go. Playing cards. This is part of culture that not everyone is equally familiar with. So if you look at playing cards, you've got half of them are black, half of them are red, not cars, playing cards. So you have diamonds are red, the diamonds and the hearts are red. There's two black suits. The black suits are what class?
Spades.
Spades and
Clubs.
spades and clubs are the black ones. So we've got spades and clubs. I'm having trouble getting black up there. Let me try it again. Not giving up yet. Spades and clubs. So the spades kind of look like a shovel upside down. Spades look like this. Clubs look like a kind of a three-leaf clover. The hearts look like hearts, and the diamonds look like diamonds. Okay, so there is an ace of diamonds. You can think of that as a one. Frodo, welcome. Grab one of each of these two sheets. One of each. So think of the ace as a one, then we've got 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then the face cards begin. The face cards go Jack, Queen, and King. So we've got 2, 4, 6, 8, 10, 12, 13. 13 cards in each suit. There's an ace of diamonds, an ace of hearts, an ace of spades, an ace of clubs. Altogether, 13 times 4 equals 52 cards. If you take out the jokers, there's 52 cards in a deck. So a deck of 52 playing cards can be thought of like this. Now, Frodo, what we're doing here, the part you missed, is that I'm going to try to argue that independent events are never disjoint, and that disjoint events are never independent. I'm making a video of this, so if you want, you can go back and watch the video to see the development of all this. But yeah, it's a good idea to take a picture so you can get a head start on taking notes. So when I ask students, are independent events disjoint? Always, sometimes, or never. About half the class said always, half of them said sometimes. No one said never. No one knew that, or at least no one raised their hand to indicate they knew that independent events are actually never disjoint, much less disjoint events are never independent. So using the context of some cards here, let's do problem 2. Problem 2. On this sheet of paper, on your main handout, from randomness to probability, part 1 of 3, the question is, are the events diamond, and instead of A, we're going to say diamond, and ace, disjoint? Question mark. Are diamond and ace disjoint? Or, in other words, is there no overlap whatsoever between event A, which is the card is a diamond, and event B, which is the card is an ace? Are they disjoint? So, what would you say the answer to this is? I mean, is this the state of reality that we have the diamonds over here and the aces over there, and there's no overlap whatsoever? Class?
No.
No, they are not disjoint. What card proves?
The ace of diamonds.
The ace of diamonds proves that there is a non-empty football. There is actually one card in the football. Here's diamonds, here's aces, and that football is populated by the ace of diamonds. So the events ace and diamond are not disjoint. Okay, so next question. Are ace and diamond independent? Question number 3. Are the events diamond and ace independent? It's a separate question. Okay, so I'm going to just give myself a little more room here. So we looked at independence starting with day 1 of this course, our survival and class independence. It's all this drama. Is there some sort of injustice occurring on the Titanic? Is it just the rich people that have a high chance of surviving? So we started from day 1 with the concept of independence. But in that very first handout, I announced that's not until chapter 14 that we're going to get an algebraic understanding of independence. So today's the day where we're going to look at independence more deeply more algebraically than we did in Unit 1. Do you remember what it was in Unit 1? Unit 1 was if the distribution of conditional relative frequencies of one variable is the same for all categories of the other variable, then the two variables are independent. Do you remember that language?
Yeah.
Survival and class are independent if the distribution of conditional relative frequencies of survival is the same for all categories of class. We worked a lot on that phrase. Now, let's look at a different way to detect independence. So, here's a plan, friends, and I'll put over here on the side. Here's your algebraic detector of independence. Let's go ahead and put it off to the side. If the probability of A does not equal 0 and probability of B does not equal 0, those are crucial conditions, otherwise you're going to be confused. Then events A and B are independent whenever, and here it is. Andrew, do you have this one? Or perhaps you know what it is. Do you know what the condition is? No. Okay, A and B are independent whenever the probability of A is equal. Go ahead and write this on the right-hand margin opposite problem 3. We're looking at whether ace and diamond are independent. Have you ever played cards before?
Yeah.
Really? Okay. So if you want to find out if ace and diamond are independent, look at the probability of A, which could stand for ace, and ask yourself, is that equal to the probability of A given B? That's the given slash. Is the probability of ace the same as the probability of there being an ace given that you know for sure the card is a diamond? It's like, I'm not telling you whether this card is an ace, but I'll tell you this much. There's a diamond on it. Does that change the probability of it being an ace? Well, come on. What's the probability of a randomly selected card being an ace? Can someone tell me the probability? Say it again?
4 out of 52.
Yeah, let's find out. Our probability of ace and diamond independent, or ace and diamond independent class, let's do the math. Let's ask ourselves, is the probability of ace equal to the probability of ace given diamond? Question mark. Are those equal? You told me that the probability of ace is 4 out of 52, which is correct. Now, what's the probability that the card that I'm holding is an ace, given that you know that it's a diamond? I'm not telling you what card it is, but it is a diamond.
13.
1 out of 13. Only one of the 13 diamonds is an ace. Now, is 4 out of 52 equal to 1 out of 13?
Yes.
Yes is correct. So, the answer to problem 3 is yes. Ace, diamond and ace are independent events. Now, remember where you got messed up. Independent events are never disjoint. Some of you said, yeah, that's always the case. Well, I've just given you 2 events that are independent. Diamond and ace are independent of each other. And for those of you who thought, well, then that means that they're disjoint. Well, hold on a second. Are diamond and ace disjoint?
No.
No. So I've just given you an example. For the always people, that's question 4. Are diamond and ace disjoint? Well, we already answered that. So let's go the other way around. Let's look at, and actually, you know what? This is going to be 3B because there's 2 ways to investigate independence. One is ace equals probability of ace given diamond. Part B, number 3B. We could also look at it the other way. It shouldn't make any difference. What's the probability of diamond? Is that equal to the probability of diamond given ace? So, would you please calculate both of these? Let's do an investigation. Write down the probability of a randomly selected card being a diamond and the probability of a randomly selected card being a diamond, given that you know it is an ace. Class, what's a probability? The unsimplified, unreduced fraction that represents the probability that a randomly selected card from a deck of 52 well-shuffled cards is a diamond. Class? 13 out of 52, which reduces to a quarter. Given that you have one of the 4 aces, only 1 out of 4 of those is a diamond. So yeah, it doesn't matter which way you check it. It's going to come out to yes either way. You don't have to check it both ways. You check one or the other. So what I've demonstrated here for you is that 2 events that happen to be disjoint, that are not disjoint, 2 events that are not disjoint, they are independent. So you certainly can't say that independence always means disjoint. They are not synonymous. Are you satisfied that I've demonstrated that disjoint and independence are not synonymous?
Yes.
Okay, now let's look at the bigger picture. Let's look at the terrain, which I think you might be able to fit onto this handout, but I've run out of room up here. And that is events A and B. So let's take a look at the events that you could have possibly, and are they independent, question mark? Are they disjoint, question mark? And is it possible? So, suppose you have 2 events, A and B. And suppose that they are independent events. Like ace and diamond are independent. And suppose we say they are not disjoint. Is that possible? Yes, we just saw an example. Ace and diamond are independent, but they're not disjoint. Suppose you have 2 events, A and B. And they are not independent, but they are disjoint. Can that ever happen? Yeah, you can have disjoint events that are not independent.
So would that be like a joker? You put the joker with that?
Well, let's take a look at an actual example. Let's take a situation where events are disjoint from a deck of cards, okay? So, and again, this is all non-zero probabilities. A and B are non-zero. Once the probability of A or B is zero, then that's a different story. Let's take kings and queens, okay, because they're disjoint.
Okay.
All right? And we want an example of disjoint but not independent. Okay, so probability of queen equals probability of queen given king. Okay, the probability of a queen, there are 4 queens out of 52. What's the probability of getting a queen given that you know it's a king? It's 0. There are no queens that are kings. So, are queen and king independent? No. Are they disjoint? Yes.
Okay.
So it is possible to get 2 events that are disjoint but not independent.
How is this not, how is this destroyed?
Because queen and king have no overlap. There are no cards that are both a queen and a king.
Okay.
So they are disjoint, but they're not independent. Therefore, queen, king are not independent. Okay? So
That's good.
So that's good. Now, let's go back to all the possibilities here. Suppose we have 2 events, A and B, and suppose that they're not independent and not disjoint. Is this possible? Yeah, it happens all the time. This happens all the time. This is the most common example where the events are neither independent nor disjoint. If anyone wants an example, I'd be happy to come up with one. But these are easy.
Like that was the Titanic one first day, right?
Yeah. Survival and first class. Okay, or just survival and class in general. But when it comes down to specific events, A and B, actually disjoint. You want to be, A would be something like first class survivor, and B would be third class survivor. So, are they disjoint? Oh, well, wait, to say they're disjoint, no, means there's some overlap. So we could say a survival and first class passenger. Survival, first class. So, that's, again, it's almost any non-disjoint category you come up with. The probabilities, the conditional probabilities will be different. Yeah. So this happens very commonly. Now here's what never happens. Independent, yes. You have independent events that are also disjoint. That's not even possible. That never happens. And that's what I tried to start class with today, is the fact that most people think the answer to this is yes, it is possible, but it's actually impossible. If you know events are independent, then there's one thing you know for sure: they are not disjoint. And if you know they're disjoint, you know that they're not independent. So that's the big message of today. Yeah.
Is it possible that we could get like a verbal or like written definition of disjoint or independent?
Well, I've given you independent. 2 events are independent. Yeah. In fact, I put
Yeah,
it.
you did.
Right, I gave you independent. Disjoint, it's much less complicated to describe verbally. It's 2 events in which there is no overlap.
Okay.
There's no overlap. That's what disjoint means. Yeah, Louis.
I know you give like the definition, even the formula of independent, but it's so abstract. Can you like explain what is independent?
Well, keep in mind that that because it's so abstract, we didn't start with it. We started with something that's much more down to earth, down to ocean. We started with the Titanic, independence on the Titanic. Independence really means the 2 have nothing to do with each other in terms of cause and effect. I mean, what's the probability of survival? 32% on the Titanic.
Oh.
Now, if survival and class are independent, then what that means in a down-to-earth explanation is that, oh yeah, on our ship, if our ship goes down, it doesn't matter whether you're first class or third class. Your financial situation is independent of your survival chances. There's an independence there. I mean, yeah, there's some first class people who survive. They're not disjoint. Survival and class.
So you're saying that when ace and diamond are independent, they are nothing to do with each other?
Yeah. I
What do you
mean,
mean by that?
in general, just take a look at this. If you want to know the probability of A occurring, and you happen to know the probability of B occurring or that B has occurred, it shouldn't make any difference. It shouldn't make any difference whether B has occurred or not. They're independent. They have nothing to do with each other. The probability of getting an ace is the same whether or not your card is a diamond or not a diamond. Ace and diamond are independent of each other. Okay. They're not disjoint, but they are independent. All right, let's go on to number. Oh, no, pretty good. All right, so we covered all that. Let's go back to Formula Central. So back to the purple sheet. On Formula Central, so far we have, if A and B are disjoint, then to find the probability of A or B, just add the probabilities. What if they're not disjoint? So, formula number 2, if A and B are not disjoint. That is, we have a non-zero football. Here's the probability of A, or here's event A, event B, and there is some overlap between A and B. Then how do we find the probability of A or B? So then the probability of A or B, we need a modification due to overcounting. Find the probability of A plus the probability of B. But because we've essentially double counted the football, we have to subtract the probability of the overlap, which is A intersect B, once, because that football has been counted twice. So we have to compensate for the double count by subtracting one count of the football at the end. Now, notice how when events are disjoint, what's the probability of A and B occurring at the same time? Zero. So you basically, so you could actually use this formula for both situations, disjoint or non-disjoint. This is actually the formula that shows up on your green formula sheet. This is what College Board gives you on your green formula sheet, because it works for both disjoint and non-disjoint. Okay? So, next. Formula Central number 3, purple sheet, number 3. These are called the multiplication rules. We just finished the addition rules, which can really be summarized by one formula. The multiplication rules focus on independence. If A and B are independent, and by the way, that means our Venn diagram looks like what?
Doesn't matter. Oh wait, no,
It does matter.
they're touch.
There's overlap, there's a non-zero football. So if A and B are independent, then you know immediately you know what Venn diagram to draw. You know they're not disjoint. So if A and B are independent, then the probability of A and B is found by taking the probability of A times the probability of B. Now, we just talked a lot about independence, and we just learned that if A and B are independent, then the probability of A is the same as the probability of A given B, that the probability of B is the same thing as the probability of B given A. But if they're independent, then those two are interchangeable. and we have our multiplication rule if they're independent. Now, the truth is it's somewhat rare that events are independent. That's a very high standard for them to be independent. So that's why on the green formula sheet the College Board gives you, they give you the formula for if A and B are not independent. This is a more flexible formula because it's kind of rare for events to be independent. Then, if you want to find the probability of A and B, just take the probability of A times the probability of B given A. Now, we are going to learn in this unit that even though this formula looks mysterious, it's really just the formula leaf equals upper branch times lower branch. So we're going to be doing a lot of tree diagrams in which we take the upper branch of the tree diagram times the lower branch, which is always a conditional probability. And the leaf that we get at the bottom of the tree, that these trees grow down, upper branch, lower branch, leaf. Then the probability of A and B is going to correspond to the leaf. Now, there's an even bigger message that you'll know that you understand all of this unit when you get to the point that you realize that a cell is a football is a leaf. A cell is a football is a leaf. That's where we're aiming. We're not going to get there today, but I want you to know that that's what you're shooting for. In fact, I'd like to have you write it down here, quote, a cell is a football is a leaf. And this will end up being a guiding principle that if you understand it, you'll probably get an A for this unit. What is a cell? Well, in a two-way table like we had in Titanic, we had first class, second class, third class crew, alive, dead, and there were 8 cells. Every probability, not frequency, but every time we filled in relative probabilities there, those were the same as the football, which by football we mean the overlap of 2 circles in a Venn diagram. So a cell is a football is a leaf, and in a tree diagram, this tree diagram has 4 leaves. So we're going to be able to see a connection between a cell in a two-way table, a football in a Venn diagram, and a leaf on a tree diagram. So that's where we're shooting for next week. For Thanksgiving break, there is no homework on Monday after break. I would recommend reading chapter 14. It'd be a good chapter to read. The video for today, for those of you who are going to go back and watch the video, it looks like just Tony needs it, will be in 2 parts. It'll be part 1 and part 2. So have a great break. We'll see you Monday.